Welcome back, everybody. So today's video is about finite differences. So we'll do a brief reminder of what they are. We already did a lecture in the previous course on finite differences. So here we'll apply them and show an example in Excel to steady flow in a confined aquifer. So here on the top left, you can see that schematic that shows you the tangent of a curve. So again, df dx. So the differential of f with regard to x is just basically the slope of that curve at that point, which can be approximated by the tangent or just the slope there. Now, if we take that same segment and we move it a little bit down, right? So this is parallel to this one, but just a little bit down. Now we have the function f at x plus delta x here and x minus delta x here, and then this function here is here. So we can approximate df by delta f over 2 delta x, which is given here. So for a first differential, you can see how graphically this works. Now, in the previous lecture on finite difference, I showed the Taylor series expansion and how we can arrive at that second differential as well. So the second differential, so the slope of the slope, if you will, of a function is given by the value, before plus the value after minus 2 times the value in the middle. So here, divided by delta x squared. So this is the finite difference equivalent of a second differential. Now this is what we're interested in because the flow equations, the Laplace equations, are always the second differential of the head equals, something, something, something. So for a steady flow, there is no time difference. So here is just one, representation of the Boussinesq equation. Again, if you remember those lectures in the previous course. So the Boussinesq equation is the unsteady, so there's a time differential, and there might be some source and sink terms here. Just to make it, make a simple example, let's assume that there's no leakage or no recharge. There is no, we're at steady state, so there's no time differential. So all we're left with is a Laplace equation. So in 2 dimensions, in x and y, right, the equivalent, we've seen that before, is just the average of the 4 neighbors as long as dx and dy are the same. So again, I invite you to go back to those lectures if this is confusing. But when we do these assumptions, so if we just take the Laplace equation in 2 dimensions, and do the finite difference, replaced by the finite difference values, then we end up with, the head at I and j, so this is x and y, if you will. The head at some location is only the average of the 4 neighbors, right? So it's the cell to the right, the cell to the left, the cell on top, the cell at the bottom, right? You sum them all up, and then you divide by 4 to take the average, and that's the value of the cell in the middle. Now here, so again, the head is the average of 4 neighbors, given the assumptions of homogeneity, isotropy, everything is well behaved. You have a square grid where delta x and delta y are the same. If all of this is true, then we have a very simple finite difference equation where the head is the average. Now, when we deal with a well, if there is a well here in the middle, now we have pumping going on, right? So there's actually a source sink terms, if you will. There's, the change in head is due to the pumping. So here at the top, if we look at this little graphic, right, if we think of it as a square cell now instead of the radial coordinates, right, we're back to our 2D plane just for simplicity. The discharge of the well, right, if the well is pumping in that square, Ij, there is flow coming from all directions. So let's take all 4 faces separately, right? There's flow from the top, right, from the left, from the right, and from the bottom. Now the flow from the top, here, the flow from the top can be written as, again, Q equals T, right, square meters per second, or, length squared per time. So the transmissivity times some face, some area. Remember that past lecture about the sleeve, right? So now this flow here has to cross this face here. So T times delta X gives us the discharge, through that top surface per unit head drop, or per unit hydraulic gradient, right? So we have to add the hydraulic gradient, and the hydraulic gradient here is the difference in head from here to here right, in that direction. So the difference in head here is just the head at the top minus the HC, so the H at the bottom, or in the middle, excuse me, H at the top minus the middle here, so that's the head gradient, the head difference, and then divided by delta y, because of course we're going this way, so now this is delta y, right? So this is the head gradient, or the hydraulic gradient, in that direction is h top minus hc divided by del y. Okay, so if you understand how q through that top face can be written as, again, t delta x times that hydraulic gradient I just described, then of course it's the same on the left, right, and bottom, right? So you just shift the x's and y's, accordingly, but now we have all four faces summed up. Now if we notice that hc is in all those expressions, of course, that's the head in the middle, now we can just collect all those terms, factorize t out, and it's just t times the head on top, left, bottom, and right, minus 4 times the head in the middle, hc. Again, hc and hij is the same, right? It's just the head here in the middle. Okay, and finally, if we divide by 4 here, right? So if we take the head, top, left, bottom, and right, we divide that by 4. This is our average, just like before, right? Remember this expression from the previous slide. So this is exactly the same. So now we have the average of the 4 neighbors if we divide by 4. And so here we have to multiply by 4 for the equivalence to be correct, right? So now this is the average. Here now we have 4 divided by 4, so 4 goes out. We have the head in the middle, HC. And then of course now we have the 4 on the left-hand side here. Okay, so this is how we get this water balance equation, if you will. Now once we have this equivalence, we can write that again, hij is basically h is here, right? So this is hij equals minus q over 4t plus h average. Okay, so this equation is equivalent, right? And so now we can write the whole expression in terms of finite difference, and this is what we have. So now we can add that well-discharged term in our equation. Now if we look at how that works in Excel, so here's a very simple Excel interface that I will put, with the course that you'll have to play with. Oops, excuse me. This is supposed to be a movie. Okay, it is moving now. Okay. So here at the top is the equation that we're considering, right? So the same equation as in the previous slide. The transmissivity here is given as 100 square meters per day. And you can see this equation at the top for the equivalent, Excel basically formula for this finite difference, equation. So you have the average of 4 neighbors. So of course you need the discharge here, and just zooming in so you can see a little better. So you can see that because you need the discharge in that equation, you need to have somewhere to read the discharge, and here are 2 different wells, 1500 and minus 1500, and everything else is 0, right? So now we have all we need. We have the transmissivity and the discharge for all the cells, and we can just run that equation, right? That same equation, the average of the 4 neighbor minus the discharge at that same location divided by 4t, t being a constant. Now here, if we go ahead and change the discharge right here, for example, let's write 0 here, eliminate that well. So you can see that Excel doesn't automatically calculate the new, so nothing has changed on this page, if you will. So what you want to do, if you don't know that, you want to turn on the automatic or iterative functions in Excel. So the way you do this, this is on a Mac, but if you go on a Windows computer, it's the same thing. You have to find those preferences and the calculations options. And then here at the bottom, not here, like right at the bottom here, use iterative calculation. That's what you want to do. When you do finite difference, it's basically a iteration. You're calculating over and over and over and over until things converge. So that's where you tell it, how many times you want to calculate and what is the maximum error you want to tolerate. So if you put let's say 100 for now, close it up, right away you can see that, that well disappeared now. Okay, that well is not here anymore. And if you go here, you can change now a number. Let's put 1500 again, go back, and you should see that it automatically calculated the new version. So it calculated 100 times because we limited to 100 times. Now if we look at a 3D view, if you will, of those two wells, you can see the two wells there as you could see them, on the top. Again, changing that to a different number, or to a minus, just to have that would be like an injection well where you're putting water back into the aquifer, so that similar to a pump and treat, if you will, that we'll do later in those lectures. So now you have, an injection well and a pumping well on the left. Now if you recalculate the sheet, and this you find in the formulas menu, if you look at this up top, you can recalculate, iteratively. So every time you click that calculate sheet, because we set the iterations to 100, it's going to do 100 more iterations and change a little bit. Now that was a very quick, simple example. Here is a larger domain where you can clearly see that circular impact of the wells and almost like the radius of influence right here on that bigger circle. So you can really see that influence of the well on the aquifer doing that radial coordinate sort of influence, circular influence. So again, two wells, and you can see the 3D version up top here. But you can have domains that are basically arbitrarily large, right? So okay, that was just a quick demonstration of how to use that finite difference methods to solve flow equations with wells. Here's a quick example of a much more complicated domain, if you will. This is mud flow. Again, mud flow is the USGS finite difference, model to solve groundwater problems. And Aquavio is GMS is a software from a company called Aquavio. And we'll go back to that in the very last lectures of this course. But I just wanted to show you that this is basically the same thing, that all they're doing is solve, on a grid, on a complicated grid, and things are not homogeneous. So now we have, different hydraulic conductivities, different formations, different rocks, different parameters in different places, but the principle is the same, which is basically doing mass balances across those cells. Okay, so this was an introduction to finite difference for groundwater flow with a well, steady flow with a well, and I'll see you in the next video. Thank you.